Good evening, mga lagan. So we have a problem here. This was sent by a second year civil engineering student in one of the universities in northern Luzon. I will just not name the school and the student itself, but yeah, he is a second year civil engineering student from a university in northern Luzon. And he sent me a couple of questions or assignments. Some of these were already answered by him, and then he just wanted me to check his solution. And then some problems he doesn't have answer yet. So what I will do now is I will group them together, and then I will some problems will take time to solve. So I'm just trying to group them together and then see how long it will take me. If it's too long, then the next problem will be on a separate video. So first question, he just wanted me to confirm his choice. So the question is about elastic deformation of a material. So the question is the elastic deformation of a material is, and then there are four um, choices. So we have to remember that the elastic deformation or the deflection, say for example, if it is a uh, so if it is a uniform load, no, say simply supported beam, so your deflection, maximum deflection is equal to um if this is W and then this is L, so this is WL to the fourth over 384 EI. So that is your maximum deflection. And then if it is concentrated, then you have PL cube over 48 EI. So the EI, this one, this value here, EI, that is the stiffness of your section or your member. So it is always inversely proportional to your deflection. So the the stiff this the more stiff the section is, the smaller the deflection would be. So the first option is, or the first choice, direct is the inelastic deformation directly proportional to cross-sectional area of the material. So when we say directly proportional, um, say for example, we have on this equation, y is equal to WL to the fourth over 384 EI. The values that are directly proportional to your deflection are this W and your length. And then the bottom one would be your, so this is directly, now directly proportional. And then in the denominator, that is the inversely proportional. So it says here, the first option is the cross-sectional area, which is area is equal to B times B if it is rectangular. Now, let's just make this smaller. So area is B times B. And then your moment of inertia, this I, no, I is equal to, no, not B, we'll just use D. BD cubed over 12. So this B times D, um, your cross section is part of the equation in getting your I. So therefore, the first choice, which is directly proportional to cross sectional area of the material, this is not correct because the area, the B and the D, no, the width and the depth of your section is always inversely proportional. So letter A is not the correct answer. Now, letter B, it says here, the elastic deformation of a material is, letter B, inversely proportional to the force acting on the material. Now, we already mentioned earlier that the directly proportional, the values that are directly proportional to your deflection are the load and the length of your member or your span. So it says inversely proportional to the force, wherein our force, W, is directly proportional, not inversely. So therefore, letter B is also not the correct answer. No? So letter C, inversely proportional to the initial length of the material. So again, L is in the numerator, which is directly proportional, but in the choice here, it is inversely proportional. So therefore, letter C is not correct as well. Now, our last choice, which is letter D, and the correct one, which is the elastic deformation of a material is inversely proportional to the modulus of elasticity of the material. So modulus of elasticity is your E. So this is the modulus of elasticity of your material. If it is steel, then you have 200 gigapascal. If it is timber, it depends on the timber species. If it is oh, I I forgot some timber species back home. You have say Biakal or um Nara, so it has different uh every timber species have different modulus of elasticity. But yeah, the answer, the correct answer is letter D, which is in a the elastic deformation of a material is inversely proportional to the modulus of elasticity. So again, also, if ever one of the choices is um, either E, modulus of elasticity, or I, the moment of inertia, is inversely proportional to your deflection, then that is the correct. Or sometimes, um, if you combine EI, this is called the flexural stiffness. So sometimes maybe the question would be inversely proportional to the stiffness or flexural stiffness of your section. Then again, that is also the correct answer. And then uh, deformation is directly proportional to your W and the span of your um, what we call this one, your member. So the longer the beam, the bigger the deflection. So that is directly proportional. So the bigger the section, where our section is at the bottom, the bigger the section, the smaller the deformation, because the deformation is inversely proportional to your cross-sectional area or um, stiffness, flexural stiffness. So I hope, so again, his choice now is letter D, which is the correct one. So I hope I explained this clearly. So yeah, you'll just have to familiarize. I guess on this in this question, all you have to do is familiarize with all the notations, symbols in say like design. What is deflection or what is elastic deformation, and then what is the moment of inertia, what is modulus of elasticity, or what is flexural stiffness. So you just have to be familiar with all those notations, and then of course remember the formulas. Then you should be okay. So I guess that's clear now. Um, If you need more like clarification, just send me a message. So he sent this via my messenger just this afternoon. So the next one, it says here, is it clear? So the next question, he already answered this one. His answer is letter, his answer is letter C, the third one. So it says the question is, what force is required to punch a 20 millimeter square hole? So for example, if you have a steel plate and then you have a you have to punch a hole which is 20 millimeter square. So 20 millimeter square. So 20 width, then 20 depth. And then on a plate that is 20 millimeter thick. So the thickness of the plate is 20 millimeter with a shear strength of 300 meganewton per millimeter or 340 megapascal. So our equation, our equation, shear stress is equal to, or I guess in theory of structures or shear strength of material, the notation is tau. The shear stress is equal to P over area. So shear stress is equal to the force P over the sheared area. Area, it could be a planar area or like a vertical area. It depends. If it's punching, then you consider the vertical area. Now we already have, or the question is P. So we have this value, we have this given, which is 340 megapascal, and then we have our area, although it's not directly given, but we can solve for the area based on the information, which is the hole is 20 by 20, and then the thickness is 22 millimeter. So we can solve for the area, and then the unknown is how much force is required to punch that 22 millimeter thick with a size of your hole is 20 by 20. So from this equation, from this formula, since the P is unknown, then we'll just use P is equal to your shear strength, right? Your shear strength times the area. Now, so this is just like a direct substitution. So we will solve for area. Now, your shared area, because this is punching, we'll just draw like a 3D here. So this is your punched area. Now the dimension is this is 20, and then this is 20, and then the depth or the thickness is 22. Now your shared area for punching is this one. This area here, this one, and then on the other side as well. So four sides. So therefore, our shared area is equal to the perimeter, right? So area is equal to perimeter. No, so we'll not confuse with the other p. We'll just use small p. Perimeter times the thickness p. Now our perimeter, so this is 20 by 20. So 4 times 20, and then times the thickness, which is 22. Now our shared area is equal to 4 times 20 times 22. This is 1,760 millimeter squared. So that is our shared area. Now, we can now substitute this equation or this value to your equation, which is this one here. Your P is equal to the shear strength times area, the sheared area. So therefore, our force P is equal to our force P is equal to 340. This is in megapascal, and then megapascal is the same as this is the same as Newton per millimeter squared. So megapascal is the same as Newton per millimeter squared. And then multiply this by our area, which is 1760 millimeter. It fits. Then our P is, so 340 times 1760. This is 5,000 or 598,400 Newton, or this is equal to 598.4 kilo Newton. So let's check his answer. 598.4. So the answer should be this one, letter B, not letter C. So this is wrong. So all you have to remember is shear area, or like P over A. If the area there is the sheared area. But if it is a if the question is compressive force, then your area should be the projected area, which is 20 by 20. But in this case, since the question is sheared based on shear strength, punching area, so the area here would be the sheared area, so which is our thickness times the perimeter of your punch hole. So again, the correct answer is 598.4. So his choice, which is 469.08, that is wrong. So I guess yeah, it's just a direct substitution. Just remember all those formulas, and then if it's punching again, if it's punching, then consider the sheared area, the punch area. So that is the perimeter of your hole times the thickness. But if the question was compressive force, then the P would be the force, and then the area would be the projected area, the flat surface, which is 20 by 20. But in this case, it is punching, and the shared area is your perimeter times the thickness of your plate. So, yeah, so the correct answer is 598.4 kilonewton. Now, on this one, the next question, this is like a, if you have like a plate pulled away from each other, and then you have a like a splice plate. This is this is in actual application. This could probably um your bottom chord of a truss. So your bottom chord of a truss is in tension, and then you have other options of splicing the, because for example, if your span is say 10 meters, and then your available material is only at 6 meter length, so you have to do some kind of splicing. So if it is steel, you could weld the member, or you could do some like bolted connections, and then if it is wood or timber truss, then all you have to do, you can do a like a bolted connection as well. You have your say it's either a steel gusset, or a plywood gusset, or a dimension lumber gusset. That's whatever is available. And then the next one, This is a possible also like possible solution is using a glue. And this problem is what it is. Like you have a glued connection um, for splicing a member. So if your available member is shorter than what is required, then all you have to do is splicing. So the question is it says here two 6-inch wide wood boards are to be joined by splice plates that will be fully glued on the contact surfaces. The glue to be used, let's just zoom this. Uh, so, so the glue to be used can safely provide a shear strength of 130 psi. Determine the smallest allowable length L that can be used for the splice plates for an applied load of 9,000 pounds. And this question is good for 2 points. No? Katihikod gamay kadto. But anyway, so again, for shear, our equation is shear is equal to P times A over A. Now this time, your sheared area is the surface between this splice plate, this one here, the yellow one, and then another one at the bottom, against your main member, this one. So if you this is in 3D, if you look at that in elevation, so this is your plate, and then there is a gap of let's just zoom this out, and then there is a gap of zero point 0.5 inch. So there's a gap here, 0.5 inch, and then your slice plate is right here, top and bottom. Now your sheared area is this one here at the um, interface between the side plate or the splice plate and the main member. Now let's just erase this one. So from your equation, shear stress is equal to P over A. Now our unknown is in the area because the area is 6 times whatever is the length, right? So right now our unknown is area, so therefore A is equal to E over shear stress. Now this is one, we have this value, and then we have this value which is 130 psi. So the question is really really random. Some questions are in metric, some are in imperial. So um yeah, 9,000 pounds the force P. So therefore our area required is equal to P, which is 9,000 over 130. Now, you have to remember that this one, the way it is drawn, you have you have two opposing force P away from each other. So if for example, if the diagram, this one is a support, then you only consider your load is only 1P and this is just your reaction. But now, but in this question, you have you have P here, and then you have another P here. Therefore, you multiply this by 2, right? If this is just like a support, if this is attached to a wall, then this P will be just a reaction. But in this case, this P is also the P in the on the left side is also an applied force. So therefore, our is equal to area required is 9,000 times 2 divided by 130. So this is 138.4615, or no, not millimeter, inch squared. So that is our area required. Now, in this diagram, we have the area would be, the contact area is what? The contact area is L, area is equal to L minus zero point 0.5, right? L, we have a half inch gap here. So we will subtract that to your total length. So that is your only effective contact area or contact length, which is L, the total length of your splice plate, minus the what we call this one, minus the gap. Now, this is L minus zero point 0.5 and then times 6. That is our area. Now, remember, we have plate in both top and bottom. So, therefore, our area, we have to multiply this also by 2. We will multiply that by 2 because we have plate on the upper portion and also at the bottom. So, therefore, our area is equal to L minus zero point 0.5 times 12. And then we will substitute this to our equation, which is this one, 138. So therefore, 138.4615 is equal to L minus zero point 0.5 times 12. So therefore, L is equal to 138.4615 divided by 12 and then plus zero point 0.5. So let's say 138 divided by 12 and then 138.4615 divided by 12 and then plus zero point 0.5. The answer is 12.0385 inch. So going back to the choices, so the answer is 12.04. This one. Oh, 12.04. So don't forget that the zero point 0.5. Don't forget the zero point 0.5 because you could get wrong answer on this one if you forget the zero point 0.5 gap, because the effective area is only this one here. Um, that is left and right of the gap. So in finding the total length, you have to consider the gap as well. So imagine if you don't consider the gap. We have the letter C option here. The letter C option is 11.54. And then if you happen to exclude zero point 0.5, maybe you can say, oh, the answer is letter C, which is 11.54. Because 12.04 minus zero point 0.5 is 11.54. So just this is I would say like some kind of like a tricky question, the tricky problem. So you have to be careful about that one. And so it's 30 minutes. So let's probably have um, one more problem, and then or maybe two, and then we will do a separate video on the other problems. So let's go. So the next question is this one here. Um, a rectangular wood beam is simply supported. I don't know if you can. We'll just zoom this again. It says here a rectangular wood beam is simply supported over a span of 3 meters, carries a uniformly distributed load of 2 kilonewton per meter spread throughout its length. So we have um wait. So we have a beam, and then the span is 3 meters, and then our load is uniform load 2 kilonewton per meter. And then it says here the allowable bending stress of the wood is 12.5 megapascal. Assume the depth equal to twice the width. What are the smallest dimensions of the beam in millimeter to carry the load? So basically the question is, we will find the most efficient section based on this criteria. Bending stress is 12.5 megapascal, and then your B, if this is your B, this is your depth, where your D depth is equal to 2 times B, right? So, so from our formula, bending stress is equal to um, MC over I, and this is for a rectangular section, this would be 6M over BD squared. So this is our equation, 6M over BD. This is B. So that is B, 6M over this. This is only applicable for rectangular section. Do not use this direct formula if your section is, say, I shape or um, um, like a composite section. No, do not use. This formula is only for BD squared, because this I, which is B squared over 12, and then your C is B over 2, and you should simplify that one. This will be 6M over BD squared. So from this equation, we have we have value for the allowable bending stress, and then we have B, which is half of your B, and then the moment. But although the moment is not different, but we can solve for the moment based on the load provided. So for the load, for uniformly distributed load simple span, your maximum moment is equal to WL squared over 8. So I assume that you are already um you were discussed with this already in prior subject, because you already in this like this is a, I don't know, probably a design or like a strength of material, I don't know, but the maximum moment for simply supported uniform load is WL squared over 8. And then you can just simply substitute all these values here. W is 2, so 2. And then L is 3 squared over 8. Therefore, our maximum moment is 2.25 kilonewton meter. So that is our moment due to the load, 2.25 kilonewton meter. Now we will substitute this value M, no? This is our M, to this equation. So we have if B, now our equation again is if B, is equal to 6m over bd squared. So therefore, this is, how much is the bending stress? 12.5. So this is 12.5. Now this is megapascal. So this is mega or times 1000 kilonewton per meter squared. No, we will convert it into kilonewton because our moment is in kilonewton meter. So the given is 12.5 mega newton per meter. So that is 12.5 times 1000 kilonewton meter squared. So this is 6 times our m is 2.25 kilonewton meter. So this is in kilonewton meter divided by B. Your B is, say, we will solve first the depth. So your B is 0.5 T. So this is your B, which is 0.5 D, and then our D squared. So therefore, this is D cube is equal to 6 times 2.25 divided by zero point 0.5 times 12.5 times 1000. So our D is equal to 6.25 or 6 times 2.25 divided by zero point 0.5 times 12.5 times 1000, and then cube root. Where's cube root here? So this is, your D is 0.1293 meter, or no, meter, or your D is equal to 129.3 millimeter. And then your B would be B over 2, which is 64.6, 64.65 millimeters. So these are the minimum dimension required. So let's check the choices. 129 and 64. 129. So 129.3. So this one, so this is our, so this is our D, and then half of that would be 64.65. So not in here. So maybe looks like there are lots of um choices here in the let's zoom this out. So there are lots of choices here. We have 129, 62.36, and so on. So basically these two are, if your D is 142, then B is 71. So these are pair, right? Which is B and B. For some reason, I don't know, maybe it's in the one of the choices, maybe not included. It was not included in the, like, when he snipped this problem, because half of 129 is 64.65. And for example, in like during the exam, if ever your choices, like in the board exam, the question will not ask you to determine um, the correct or the yeah, the correct answer or dimension, but it will ask like it is worded in a manner like which one most nearly gives the correct answer, sometimes like that. So if it's not there, whatever is the closest one, that's the answer. So sometimes there are questions where like the choices, the difference between the choices are really small. For example, on this one, this is some kind of a tricky question. The first one that or the last one that we answered, where if you did not consider the point 0.5, the answer will still be there. So you have to be careful with that. So on this one, so again, the depth is 129.3. It's in here, but for some reason, half of that is not found in the choices. Maybe it's somewhere below that was not included when he snipped the um, problem. So it's 41 minutes now. So we will continue the discussion with his questions in the next video. So yeah, if you have questions, or if you want more like clarifications with regarding of how we this come up with all these question answers here, just let me know. So see you in the next video.